Hey, welcome. Today, we're going to peek behind the curtain at the invisible tech that pretty much runs our modern world. I'm talking about sensors, these tiny little things that turn physical reality into digital data. But here's the big question. How do we actually know we can trust that data? Well, that's what we're here to find out.
So think about this for a sec. You've got your car's airbags, a life-saving device that has to work in a split second, no questions asked. And then you have your phone's camera, the thing that captures all your memories. They seem worlds apart, right? So what's the common thread?
And there it is. They both rely on sensors that have been tested to perfection. Whether it's the accelerometer that feels a crash or the image sensor that sees the light, their reliability is absolutely no accident. It's the result of a super intense and careful process. And that process is what we're diving into today. So, what does sensor testing even mean? Well, before any sensor gets to go out into the world and do its job, it has to prove itself. It has to earn our trust. And that process has a whole rule book. Okay, the keywords on this slide are everything. It's not just about does it turn on. It's about making sure it performs accurately, reliably, and consistently. Think of those three words as the absolute pillars of sensor testing. Without them, you've got nothing.
And this really shows you that testing isn't just a simple pass-fail. It's more like a deep investigation. Engineers are trying to map out the sensor's entire personality, how it behaves when things are calm, how it reacts when things get crazy, and even uncovering its tiny little quirks and flaws, all to make sure it's absolutely the right sensor for the job. And to really get to know that personality, testers have to look at it in two totally different ways. You can kind of think of it like putting the sensor through both a marathon and a high-speed sprint. Each test is designed to uncover something completely different.
So on one side, you've got static testing. This is the marathon. How does the sensor hold up when the conditions are stable or changing really, really slowly? And on the other side, dynamic testing. That's the sprint. What happens when the input changes in the blink of an eye? You absolutely need to know both. Let's dig into static tests first, starting with the big one, accuracy. This is the most basic question of all. Is the sensor telling the truth? I mean, a small error in a medical sensor could be a disaster, right? Or in a plane's altitude sensor, forget about it. Honestly, if a sensor isn't accurate, nothing else really matters. Next up, we've got linearity. Now, this sounds a little technical, but the idea is actually super simple. You want the sensor's reaction to be predictable. If you double the input, you want a predictable change on the output. A nice, straight-line relationship just makes the data so much easier to understand and work with. Now, this one is really fascinating. Hysteresis. Picture a thermostat. Does it show you the exact same reading for 70 degrees when the room is heating up compared to when it's cooling down? If there's a difference, that's hysteresis. It's almost like the sensor has a little bit of a memory of where it's just been. So how in the world do you test for that memory effect? It's actually a pretty cool process. You basically take the sensor on a round trip. You slowly dial up the input, let's say it's temperature, and you record the output all the way up. Then you slowly dial it back down to the start, recording all the way. If there's any space between those two lines on your graph, boom, that's your hysteresis. Okay, time to switch gears to the sprint, dynamic testing. And the undisputed star of this show is response time. When something happens in an instant, how fast does the sensor actually notice it and report back? That airbag sensor we talked about, it needs a ridiculously fast response time, but a thermostat in your house, it can take its sweet time. It's all about matching the sensor's speed to the job it's got to do. So a sensor can be perfectly accurate and super fast inside a nice, clean lab. But what happens when you throw it out into the real world where things are messy and unpredictable? Well, that's when it faces the ultimate challenge, trial by fire and ice and a whole lot more. This right here is basically boot camp for technology. Can it handle scorching heat or freezing cold? What happens if it gets wet? Can it survive being shaken around inside a car engine? Will weird radio signals mess with its readings? A sensor doesn't get approved for duty until it proves it can take whatever the real world throws at it. All right, so our sensor passed its accuracy tests, its speed tests, and it survived boot camp. We're all done, right? Not quite. There is one final, incredibly important step, validation. This part answers a slightly different question. We know it's a good sensor, but is it the right sensor for this specific job? And there are a few ways to figure that out. You can compare its readings to a gold standard device that you know is super accurate. Or you can do what's called cross-validation, where you get a few of the same sensors and see if they all agree with each other. But maybe the ultimate test is system-level validation. That's where you put the sensor into the actual final product and test the whole thing together.
Okay, I know we've covered a lot of ground here, so let's make it all crystal clear and walk through a real-world example of how you test a simple temperature sensor.
So here's how it works. You put the sensor inside a special chamber where you can control the temperature perfectly. Right next to it, you place a high-precision thermometer as your reference. Then you just slowly crank up the heat step by step, and at each step you write down what both the reference and your sensor are saying. At the end, you plot that data on a graph. And that one simple line tells you pretty much everything: how accurate it is, how linear it is. It's a simple idea, but unbelievably powerful. And really, that's the entire journey. We take something that happens in the physical world, a change in heat, motion, whatever, and we put it through this whole demanding process of testing and validation. What comes out the other side is an electrical signal that we can actually truly trust. It's literally the science of creating certainty. You know, when you think about it, this whole process is way bigger than just engineering. Our entire future, from self-driving cars to medical breakthroughs to exploring space, it all depends on this science of trust. It really makes you wonder, as our sensors get smarter and more reliable, what's the next huge frontier they're going to help us conquer? What new things are they going to let us see? Thanks for joining me.